All right, everybody. Thank you, everybody for coming. My name's Ethan Hoban. I'm the president of Eta Kappa Nu, the Electrical and Computer Engineering Honor Society. And tonight is our third tech talk of the semester, which is Introduction to Automated Target Recognition. And that'll be given by Sean Mitchell here, and he'll introduce himself momentarily. One last call before we start the presentation. If you haven't signed in, please do. Otherwise, we'll get started soon. And thank you all for coming. And I will go eat my sushi in the back. And once Sean sees all the phones go down, he can start.
See one phone over there unless I'm blind. We good? Signed in? Okay. Alright, so this is the introduction to automatic target detection, recognition, and tracking. It's not just tracking, we're going to talk about a couple of other things that get us to tracking targets. So we're going to talk about detection. We're going to talk about detection with the lens of, no pun intended, of computer vision. We're not going to consider radar for object detection, but the recognition and tracking that we'll talk about later into it, principles of if you are detecting with radar would also apply there. I'm just not a radar person, so I'm not the expert on that. And we have some examples if we wish to look at them later. Conclusions, rules of thumb, lots of fun stuff. This is a good lecture, I think. There's a lot of useful information. So about me and why I'm teaching this there. I'm a UNH grad, 2020, worked at a few companies, mostly in robotics, AI, ML, GNC, software architecture, but I've done a lot of vision stuff in this town. That's actually a plain drone thing that I'm working on right now in my current job. I'm a master's student here, finishing in December. I do a lot of software, electrical, just across the board. I've done a little bit of everything there, but I like robots, and vision on robots is pretty common now, so have a lot of experience with that. So tonight, basic computer vision stuff. Hopefully people have know a little bit about computer vision by now. It's kind of ubiquitous. Object detection, recognition, tracking, and just trying to give you some concepts and foundations that you can take to future classes and future jobs, hopefully. A brief disclaimer. You can blame Ethan for this one there. I have worked in these technologies, so just throwing this out there mostly to cover my ass. This is all publicly available sources. None of this is classified, CUI, anything restricted, no portion marking. Anything in here is available, white papers, textbooks, practical experiences. You know, you're not learning anything you're not supposed to know. I'm not telling you anything you're not supposed to know. Is a caveat, not all work that uses target recognition is classified or considered sensitive in our local industry because we have missiles, drones, and navigation systems. A lot of it is, so just be aware when you're working with some of this stuff that you may be skirting into classified space, or if you want to work with it, consider that you're probably going to need to get a clearance and, all the fun security things that come with that. And I have some sources and textbooks at the end of the slides, so, further prove that. So, object detection. So starting with computer vision, it's a type of artificial intelligence. It's not really what you would think of if you think of a deep, like a deep learning network, but it's still kind of an artificial intelligence approach, but it allows computers to recognize and analyze visual information, as opposed to binary, voltage impulses, things like that. It often includes filters to process imagery into a form that we are used to dealing with as engineers, so numbers and data, integers, floating point values. On the right is kind of the process flow that computer vision normally goes with. It's very generic. A frame comes in. A frame is a single instance of, it could be video, could be an image, could be whatever. It goes through a series of filters that can be from 0 to as many as you can computationally handle. There is a limit. They are pretty expensive computationally, and that gives you processed imagery. Very simple there. So, in case anyone is unaware, this is how a computer actually sees most imagery. It usually is stored in an array, 2D matrix. Each index going down, I comma j represents a pixel, and the value at each of these indexes, these indices, represents a color intensity. So for black and white, 0 to 255. And you can extend that to red, green, blue if you just replace what's inside that index, that value, with basically a tuple, red, green, blue. Each one, 200, 200, 200 is some color. I don't know which one off the top of my head. And that would be your color. So this is how, if you put an image into a computer, it's how you store it. This is what it sees, and this is something we can actually begin to work with. Also note, because this is stored in a matrix, accelerated computation is possible. Things on GPUs, things with Torch and CUDA, all that's possible because you can put this in a tensor, you can throw it on your GPU, and it's just much faster. So very convenient way to store images. Our object detection is the concept of extracting features from the previous imagery that we were showing and using that as data. So, going back to this one there, you would extract features and you would care about the features of the white pixels, basically making that 8. That would be the features you'd care about extracting. This is a very rich field of study. I'm not going to go nearly as deep as it probably deserves there, and there's a lot of ways to do this with and without, machine learning, thinking about a deep learning approach. You can do it very classically too. That's how we're going to do it tonight. We'll talk about some deep learning approaches, but this is going to be done with some very classic approaches. So, like I said, no deep learning in this section, but how do we get objects from an image? How do we get from these people walking, the bounding boxes, get all the stuff that from that? This is kind of an algorithm from it. So on start on the left, you have an image frame, video frame, whatever. This algorithm, if you just looped it, would work for video. You can convert it to grayscale. This reduces color complexity because if you think about the amount of information that's actually in color, it doesn't necessarily contain information that on structure. It's relationships there, and you do care about that, but if you're just trying to say, what's the structure of this person, reducing this to a black and white can be convenient. So, there will be a chain of images after this that kind of shows this a little bit better. So you then can do a blurring, a Gaussian blur, any type of blur you really want. The point of this is to soften faint details in the background. So if you have something in your foreground, a tank, for example, and you have stuff behind it, the blur can kind of soften that out. So when you start looking at edges and thresholding, it doesn't saturate, and your detections don't go, oh, there's all these objects out behind it, because you really only care, about what's in front of you, your target of interest, your region of interest. So you turn to grayscale, you blur it, you can use that to do an edge detection and say, okay, now, you're making kind of an assumption here that, okay, anything that is sharp edges is maybe an object of interest. Perfectly flat wall, like this may not have a lot of interesting things, but like if you put, me in front of it, I have edges, I have, defined features that makes me a object of interest for a detection algorithm. So it can do that. Thresholding kind of does the same thing. Edge detection and thresholding are kind of interchangeable. Thresholding makes a binary mask that you can use to kind of filter and start selectively doing regions, but they kind of serve the same purpose. You can use one or the other or both. And then you can make a bounding box around it, which is these fun little green things. And then you do what's called non-maximum suppression. There's actually a few ways to do it, but they all serve the same purpose of reducing overlap of your bounding boxes. Because if you take an algorithm like this that isn't, aware in a deep learning sense, you're going to have boxes that overlay each other and have boxes within boxes within boxes. So non-maximum suppression kind of says, okay, I'm going to get the largest box, the most prominent box around a target. You can do things where you merge boxes, you can do all sorts of algorithms, but they all functionally try and reduce the overlap and the error of the bounding boxes. So, let's look at this image. This is from Google. Again, not giving you information you can't get anywhere else. Of this tank. So we're trying to process, and we want to detect, ideally, the tank, or parts of the tank there for, let's say a missile, a targeting system, something that would go, oh, hey, that's features we care about. So, turn to grayscale, and you can already start to see that, okay, now this image is a little bit simpler to process than this one that has blues and greens and all these colors. So, take a grayscale. So then we can start to blur it a little bit. And if you notice, like the trees in the background, some of the background features, the foreground tank is still pretty there. You pretty much still get the gist of what's happening there. But the trees, the definition, it blurs away, which that keeps the algorithm from just getting confused, essentially. So, grayscale, blur it. We're going to do edge detection, and see, now that we've done the edge detection and we blurred everything, you really only get these sharp outlines. As again, we're assuming that if it has heavy amounts of edges, it's a man-made structure, so for military purposes, that's convenient. You get this structure here, it's like, oh yeah, here's just a tank. So you now detected edges. So, and now we get bounding boxes. And now you see what I was saying about the non-maximum suppression and the overlap of, if you do that, you get all of this mess. It's like, okay, which is technically true. You could probably lob a missile at one of these and probably have a pretty good shot of hitting something man-made. So then when you add the non-maximum suppression, it's like, oh, there's still error, and that's just because you don't have a semantic understanding, which is where like a deep learning approach would start to give you some advantages. But you can see the difference there. The overlap and all of these inner boxes kind of fades away because they're like a sub-region of the larger boxes. So that gives you, that kind of explains that algorithm. Some more examples here. And the other thing that I think is interesting is the one on the right. Again, nothing that you can't find on Google. You can add coordinates to this there. So like for the ships there, and hopefully by now, some people are thinking, wow, that would be a great way to target something. And send a missile downrange there, wow, there's a target with some coordinates, and you can convert that X, Y, and these pixels to something that is representative of, kilometers or, meters or, angles, anything like that, which you can. That's part of some of the leading guidance. There's your, what the camera secret is going to see. It says, hey, that's what I hit, before it gets blasted by that carrier fleet. So that's some object detection. So, and again, all of this was done, I do everything in OpenCV. Everyone does it in OpenCV. If you like this stuff and you haven't used OpenCV, you need to use OpenCV, because it gives you everything you need to do most to this. And there's code that I'll pass around if you sign the little interest sheet there. It uses OpenCV. It's just Python, OpenCV, and NumPy there. And you can do all of this. Just load an image, load a video, and you can start generating stuff like this. And all these images came from this exact algorithm. And I have this in the code. They all generated these 3 or 4 images easily. And like I said, you could easily identify something from that. So that's a little bit of a yes.
So, so we were talking about how, like, in the background, right, objects that are further away, like sharp. So you have a program that tries to find sharp edges, and you have, say, rather than the camera being like close to this tank that you're trying to hit, it's 500 meters, 1,000 meters, a couple kilometers back, and you have this blur in the program. How does it detect from that range when, a couple miles away or whatever? It's just all blur. It's just one.
Yeah, so that's where selective blurring, you might have a camera lens or a seeker that says, I'm going to consider a wider seeker field of view, consider a more center point, focus in and say, maybe scan and be like, okay, here's some fidelity just in this space. It's also something where if you do, this is a non-deep learning, deep model approach to this. You can easily get into using, I'll post, and I'll talk about some of the, modern approaches to this technology that do use deep learning, and they avoid it by doing what's called semantic analysis, semantic recognition, which essentially says it builds the relationship frame to frame based on what's around it. So as opposed to this approach, which says I'm trying to filter out everything until I just have something that is a man-made edge object, that actually tries to look at an image and go, okay, what's the relationship between, the tanks and the ground? Okay, I see ground everywhere and the tanks are sitting on it, so it can make inferences, which is still a deep, deep network. It doesn't know things, it makes inferences. It's statistically different. But yeah, in that scenario, this may not be the algorithm you want to use. And you don't have to. You can play with this. And I do recommend it. You can pull out like the blur section and see like, okay, yeah, this changes the performance. You can also, because a Gaussian blur is kind of just throwing noise onto an image, as a filter, you can tweak, your kernel. You can actually adjust how much blur you add. You can add, a bunch. You can add just a little. So, it's a complex question that depends, but it's not as simple as you have to blur or you don't have to blur. You can adjust it, you can make it, you can just blur kind of the outer, leave the center of it unblurred and then blur around it and, scan and go, hey, there's a target, and then blur around it, the area you don't care about, the non-region of interest. So hopefully that made some sense.
Quick point. Sean mentioned it. At the end of the presentation, there'll be another form. If you fill that out, that will give me your email, and it'll allow me to email you the full slide deck along with any demo code in our GitHub repository that Sean produces.
So definitely we recommend doing that because some of the code's kind of cool. So object recognition. So object recognition is taking this to the next step, specifically identifying the information that we've detected. So if object detection is something there, it was that tank there, object recognition says, is that a tank or, is that a school bus of orphans? You probably don't want to put. So, and you can see here in this, this idea, it's detecting an object, but it's going, hey, that's a bookshelf, that's a stove, that's a TV monitor. This really is the concept of trying to understand the context relations between imagery and within frame to frame, as a video moves forward. So, there's a few ways to do this. I won't say there are wrong ways, but there's kind of one way people still do. You can match imagery based on templates and broad characteristics like size, color, shape, etc. You know, if you're sitting there on the ocean and going like, oh, you know, if it's above the water and it's a large object, it's going to be gold or diamond, you know, a kraken or something like that. You can match features, you know, that's what we were doing with the previous example of matching edges. You know, like you're making the assumption of, you know, oh, if I'm out in the middle of a field, in the middle of a war zone, and I can detect something that has a large something man-made. Finally, you can use a neural network to learn features of the image. This is pretty much the way it's done. It's the way I've always seen it done in my career, and you know, it's a little expensive computationally. We've learned all of this, but because of this is very simple. Because it basically allows you to do semantic segmentation, semantic recognition. So on the right here, the right, you have image recognition, and the top left is saying, hey, you have some sheep and you have a dog. Object detection is saying these are your objects in it. Semantic segmentation is saying, okay, of the objects, put them into categories, categorize them. So red is dog, blue is sheep, and then instant segmentation just is kind of its own thing that just says which one is a unique object. So it's combining segment and object detection. This is where having something like a deep network that can actually build those relationships, because deep models are really good at learning complex behaviors and relationships between high dimensional data. So if you think of that original image of the number 8 with all the numbers, but think about something as complex as like this image with colors and multiple features and moving in, like there's all those values in there. Those are complex relationships that are correlated together. The sheep are in a pack, they're in a region, they have similar colors. There's a correlation between all of that a simple algorithm just does not capture. I mean, you can filter this and you probably get something similar, but it's not the ideal way. The ideal way is to actually use one of this. I won't go full into how convolutional neural networks work. I have a book here that has some recommendations on because it's one of the guys connected with was it OpenAI? Is he? Oh yeah, it's OpenAI, one of those guys. But basically, a convolutional network is a deep network model kind of designed for imagery. So starting from the left, what it does is it sends in a pixel, and I'll show what image convolution looks like in a couple of slides. But it takes an input, it expands out, tries to build features, and then reduces them to simplified features, which then on the classification side says, hey, I know that I have 100 options I could be, different types of dogs, whatever. And then it can give you an output that says it's that type of dog. Except dogs could be, all known tanks currently deployed in theater, that type of thing. So the way that works is it does what's called an image convolution, which if a lot of you probably have seen convolution in your control equations class or your calculus classes by now. Maybe, I don't know. But essentially what this does is it takes a pixel and it says, okay, for this red one in the top left with this index with 3 in it, you're going to expand out and look at all of its neighbors and build a feature map around that. So you're kind of expanding out a single pixel into a larger image, running it through the kernel, and that gives you a single value. So the value you actually get from the network and from the analysis of the network is not just like a straight one-for-one. It takes into account what's around it. That's how it builds a relationship. It builds the semantics. It says, hey, this is why these things connect, why those sheep are in an area or region of interest together is because when you look at those pixels, look at these, they are all kind of adjacent. So if you're looking at a single pixel, it doesn't know what's around it. But when you start looking at like, okay, all these are together, you can build it some form of relationship. So it runs through that, it convolves everything, pooling tries to reduce that image into simple, understandable, digestible parts, and then it says, okay, now this image, there you can go and plane, whatever, and it will give you an output. So you can use that to go back to getting something like this. If your training set says notebook, laptop, glasses, coffee, iPhone, and it goes through, it takes that image, it convolves it, it pulls it, and you query it, it goes like, okay, yeah, I detected that box you gave me contains the bounding box from your previous detection, and go, okay, yeah, here's just that. And you can build something off of it like that. So that's a little bit about that, and yeah, this have a video frame coming in, object detector, which a lot of networks that do this now with the object detection. And it goes into the image convolution, it pulls it, it compares it to the training processes, and then it gives you just what kind of object. This one, you'd be able to identify that's a carrier, that's a destroyer, helicopter destroyer, that's a tanker, etc. You wouldn't have, it could identify high value target. Object tracking. This is what most of actually kind of came a little bit from. Object tracking is the concept of following an object, including its state information between frames and moves through time and space. So the radar aircraft supplies overhead and security a moving person to the store. Because like I said at the beginning, this is the stuff that applies to more than just this, these approaches can apply to any detected object. So if you have a radar detection, then you can use this in the simple foundational algorithm of how you might start to track it and follow it. So, detection is something there, and recognition is what is there. Then the question that this answers is where. There's a lot of ways to do object tracking. This is a pretty simple one. This is available knowledge. It's called central tracking. Central organization one is unfamiliar. Is basically just kind of the central point of a geometric shape. It represents an average location of all its points. So, everything ever has a centroid. It's like this is kind of center of gravity type thing. So, centroid tracking involves tracking an object via its centroid as it moves frame to frame. As we go forward with this, what we're going to do is we're going to consider our bounding boxes that we've detected and we've generated as a geometric object, and we're going to compute the centroid and start trying to track based on that. So just keep that in mind. So that means that our algorithm must store the last position of the object's centroid. It must kind of know if this is considering a single target tracking algorithm right now. It must know where was the object last, and then it must go, okay, so I know my object was last. I have all of these 20 objects up here. I know the current locations of that. Update the algorithm with that. Compare where the last known location of the target was versus all the locations you just computed, and then decide if one of those is a reasonable assessment that you could get from where that last target was. One of the, so if you're 20 points and they're all 2 miles away, and you're tracking a moving person, probably not it. But if the tracks as half a foot away from where they used to be and all of the other rooms, you can make the assumption of okay, that's probably that person. So it's not a foolproof method. There's a way to do it. It's a very simple way to do it. And if you need to track something, it can work sometimes. It can usually work. It's kind of the bare bones basic approach. So this is more visually explained. You have a video frame coming in. You have a detector. You're getting a centroid of all the bounding boxes inside that frame, getting current positions, taking differences, and basically looping over that. And that will give you, a tracked object X, Y, Z. And visually, you have an object moving, and this is what you're trying to track. Is just, you're getting a position output, and it probably looks a little bit. Probably going before we get time to go. I should have started this before I did that. Yeah. See if that works. But I'll leave that up because that's probably a better. Do you have any quick questions while I turn my laptop on? No? Okay. Sure, this is going to break the recording, but the camera doesn't work anyway, so.
Yeah, so plug that up.
Yeah, just getting my files up.
All right, I see your screen.
Is that okay? Does this do what I think it does still? Okay, yeah. So this is that algorithm that I had up there earlier, working in per person, is showing the numbers. So what this is doing is every frame it's taking in the whole frame one by one, and I can actually probably slow that down. But you know what you can see is those numbers that are falling off. Those are your track IDs. So yeah, we'll just loop back through. Or do I have to rerun it? Probably just slow it down. So it's keeping track of about 10 different features, you know, boxes on this. And this is where the algorithm does fail a little bit because it's kind of capturing stuff on the inside of it. And this is where having like a more sophisticated algorithm would handle this in a better way. But if you were still lobbing something at that, you'd be able to track it. And you can see as it flies out of, you know, frame, the tracks go away. So it has a time period that's like, oh yeah, you know, I don't see that anymore. Deregister that track. Because it's registering and keeping a history of things. And then if it's not there for like 10 frames or however many, you know, get rid of it. But, you know, that's kind of what the algorithm is supposed to do. And not what I meant to do. Oh, there we go. Yeah, so see, if you do that and you start pulling things out of frame, it comes back in. I don't know where the actual, it's one of those numbers there. But this is supposed to be a way that, yeah, see, this is where the algorithm gets a little funky. We're not going to do this one. This one's not the best one. Yeah, there we go. What's the, which was it? Oh, PC. There we go. There we go. Okay. And we can come back to that at the end and we can look at that more if people want to. But this is that same algorithm. So it's getting centroid bounding boxes, it's detecting current positions frame to frame, taking differences, you know, you're looking at the last known positions of tracked objects, and it's storing those as you go frame to frame further into the video. And of course you can also do this with imagery, static imagery, but you know, what goes that to track? So it was kind of a full example, and this is what I was running in its full, is you have the object detector running, grayscale, blur, edge detection, bounding box, suppression. Does the object recognition would go in there? I did not include that because, you know, that's quite a bit of effort if you don't run that with a trained network. And then it goes into your tracker, and then you basically just keep looping through this, and at the end of the day, you get, what is that mouse? Okay, it doesn't, there it is. This mouse here, you get the tracked object XYZ, and that's really what you care about out of something like this, is what your positions actually are. So, beyond that, and this is where it gets really fun, this is what you would actually start doing if you were trying to make this for a robust system. The simplest one would be SORT. It stands for Simple Online Real-Time Tracking. It is a Kalman filter-based frame-by-frame state tracking algorithm, and I think I have the GitHub link to it there. There's some papers on it too. But it's as opposed to viewing things as edges, it's viewing them as a combined fused Kalman state. Deep sort is sort with deep learning, so it's Kalman filters and deep learning. Fairmont and Transmont are some newer approaches. Fairmont is a deep autoencoder that's comparing, it's reading in data and making a assumption about it and challenging against it. And then the Transmont, I'm not as familiar with, I can make inferences on the transformer model, but it looks at both space and time, so it has some time elements in there. Byte track is interesting because it tracks all objects and not just high confidence objects. So as opposed to having that reduced bounding box subset, it would track everything and make inferences based on everything it sees. It's still surprisingly efficient. And YOLO VX is actually the one that if you go into a job in town, that's the one you're really gonna see. Mostly because the license doesn't allow commercial use without rewriting it yourself or paying Ultralytics money. But it's kind of the gold standard. I don't know, has anyone ever used YOLO or heard of it for anything, aside from you? I know you have over there.
I used the first one.
Oh, you used V1, wow.
In his original
you
paper.
Used it too? Yeah.
Space Hardware Forecast Director only uses YOLO.
Oh, cool. Yeah, so there's about I think 11 versions now. I think we're waiting on a paper for 11 so we can actually re-implement it, for free, quote unquote. But it stands for you only look once. And the idea is you take a instantaneous snapshot of your image frame and look at that, get your semantics, get everything, and you're not storing a bunch of history, you're inferring based on behaviors and what it sees. But it's really efficient, it's really fast. I mean, you can do like 60 hertz video and stuff like that. And it does tracking, detection. I think I actually have the link somewhere for it. We'll come back to that. So some rules of thumb before we get to the links and some of the other stuff. This is an extremely computationally expensive process, especially with computer vision. Because images get huge and they get fast. I've seen cameras that are 60 hertz, 120 hertz, high-end stuff, and that's a lot of data to process. And then if you're detecting imagery on top of that and you're tracking objects on top of that, even, it just gets worse. You get slow. And the GPUs help improve that, but they also increase costs, they increase power requirements, they increase space requirements and vendor requirements, because the Army and most military bases do not want you flying with hardware that does not come out of the US. And let me assure you, finding graphics cards made exclusively in the US is difficult. That's not something that's easy. And the lead times on the ones that are not 1 week shipping. Just bitching about my job a little bit there right now. If you can reduce your problem space, you'll see higher performance. So reduce your bounding box. Would you put limits on how many targets you actually want to track at a time? Use the object recognition to try and reduce the things you think are meaningful. If you have 100 objects and 3 of them are tanks and the rest are trees, don't shoot the trees. Don't do that. We need those. And consider how many objects you actually want to track. Think of your problem space. Your missile flies forward. Your objects behind you probably don't matter too much, mostly because that's probably you. And it can also only hit a handful of targets. You might have a warhead with multiple kinetic vehicles on it, like a MIRV type of thing, but it still only has so many things in it. Your shotgun shell only has so many pellets there. So if you have, you can hit 100 objects, don't track 1,000 objects. I mean, you can, but something to consider there. So here's some of these links are interesting, but these are sort, deep sort, Ultralix is YOLO, Fairmont, and we can go through those at leisure if we wish. So some suggested reading, if you found this interesting, if you liked the machine learning stuff, this book here, Deep Learning, Ian Goodfellow, he's a research scientist at OpenAI. So pretty good book. This covers pretty much everything you would want to get started with machine learning, linear algebra. Pages that start together. Numerical computation, basics, regularization, deep learning, convolutional networks, recurrent models, autoencoders, all the fun stuff, everything. This is kind of if you need a one-stop shop of it, it has a maybe poorly aged quote from Elon Musk on the back there, but has Yang LeCun, the director of AI research at Facebook. So it's a good book. Pattern recognition and machine learning is also a good book. It focuses more on how networks follow patterns, and that extends very well into image processing. That feature extraction, image processing for computer vision is really good too. That gets into how you pull stuff out of computer vision. Last one, some of you in the WE department maybe have seen this book there. I use this book a lot. I use this book still. I used in 382, 3, 4, 5, 6 in my graduate classes. It's a good reference to anything that is a signal or a system. Do not get rid of it. I know it's probably cliche, but this is a good foundational math book for anything that you're going to be doing with image processing, signal processing, any of that. In the Math 2 extensive deep learning, highly recommend that. So, and if you also enjoyed this, I'm sure this is not all the classes I know UAH teaches that are connected to this. This is just what I know of the CS and the E department. If you're an undergraduate for E, you're going to be taking most of those that you kind of get that free with your major. Most of them are pretty cool. If you're into the CS side of things, there's some intro to computer graphics sequences in the CS department that talks about computer vision and how vision and imagery data is stored in a computer. At the graduate level, there's a digital image processing class that Dr. Pan teaches. I've not taken that one, but I have taken his digital signal processing class, which they offer in summer, actually. It's a good 5-week class if you like graduate signals, and a lot of that work overlaps with image processing. Images and signals are kind of functionally the same thing. In the CS department, CS 637 is deep learning. I took that one. very good class, very hard class. But you'll learn a lot, and you'll make deep networks from scratch without torch and without tensors. You're make them in Python with matrices, and it's gonna suck, but it's a good learning experience. And then they also teach 640, which is a machine learning class, and I think Pan teaches some ML stuff occasionally too. But these are the type of classes you'd be wanting to take if you want to get more into image-based and vision-based ATR and tracking, signal processing, things like that. Also some food for thought here. You can get into this really cheap because pretty much everyone here has a webcam on their laptop, and that's pretty much all you need. You also can buy a Raspberry Pi and camera, 8 gigahertz, for probably about $80 right now, and you should support it. It's cool. And it will run OpenCV, just like your laptop. And clever projects are great ways to learn, and in my experience, have been differences between getting jobs and not getting jobs. And, you know, being the undergrad or the grad student that comes into your job interview and going, I've made my own security system, or I've made, you know, a tracker for the sun from my solar panel, or something like that. That looks good. People like that. Yeah, so question, I'll go back up to some of this there because that was some interesting. People were asking about YOLO. Yeah, I have links to a lot of the algorithms there that these would be more how you would actually start to do tracking. Just have papers, yeah, PDF. That's what I actually care about. Yeah, and all this is out there, and it's a constant field of research, and that's not a long paper. But for the most part, yeah, it has metrics of this, you know, speed in milliseconds, all of these. If you're going to do something like ATR, YOLO is probably the professional. Yeah, see, it has the different metrics of its performance there, up to from V5 up to 11. You know, highly recommended. The only reason it's not the best is because their license is restrictive. But yeah, they excel at object detection, tracking, instant segmentation, image classification, and pose estimation of, you know, what orientation is someone looking at. Because you have to remember, when you're doing detection, you're essentially getting a view like this for an object that might be at an angle, and that's where homography and some fun stuff like that of converting that angle and your flight angle to where they're orthogonal to each other. Yeah, let's see what else do I have on here. PyTorch, OpenCV, these are how you actually program this. Yeah, so we can have a question and answer section. Fill out the form for the code, and if you wish to talk about any of the other links, yeah, a lot of people got phones after that.
Tell them about the Lido stream.
The what now?
Tell them about the Lido stream.
Which one?
Dealer's choice.
Oh, so the first job I had out of undergrad, back in 2020, was with Lidos. They have a very strong vision navigation, vision science department. I was in that department for about 2 years. Left because I had some friends that wanted to make drones from scratch there, and that was more fun at the time. And it was more fun in general. But if you're interested in that type of thing, Lidos has a very strong group. They have a lot of contracts. I worked on stuff that was for, you know, Office of Naval Research, worked on stuff that flew, worked on stuff that was on soldiers' backpacks for GPS-denied navigation, ground vehicles. I know they have some space-based applications in that group. You know, they had more contracts than they really knew what to do with there. But if you're interested in that kind of stuff there, and, you know, that excites you, then, you know, I perpetually see, you know, I think the title I see them advertising is robotics navigation engineer. If you see that on LinkedIn or something, and for Lidos, you know, you like this stuff, definitely, you know, give it a shot there. So, you know, I don't really have anything bad to say outside that group there from a technical perspective. They were all there. It was filled with PhDs. I think that I was one of like 3 people that didn't have a master's out of 50 people. It was like, and everything else was cut between doctorate and master's graduates. So a lot of knowledge and a lot of people that had been working with specific cameras for 40 years and know everything about it. So if you're interested in that type of stuff, you know, give them a look up. Yeah, so I'll leave that up there. So any questions or anything we want to go back over? Yeah, hi.
I'm a bit interested in the convolutional neural networks and how, like, they're actually done. Is it like done with like YOLO or like what was the other thing?
So YOLO is the pipeline, the actual ML pipeline of YOLO is, elements of it are convolutional and it uses image convolution, but it's actually, when you look into the, I can probably pull it up there, it's not that simple, yeah, that's probably the nasty image that I was trying to find. Yeah, so can I get that bigger, maybe? Yeah, so it's not just a convolutional network for something like YOLO. This is YOLO V11 there. You have convolutional segments there, but you also have shortcuts that go on these backbones to various other things that do upsamples and concatenations, have all these other, and these are all like elements there that run. So, you know, it is technically convolutional. But it is, they've expanded that concept of what it means to be convolutional, and taken out, that's how it can do real-time tracking, detection, segmentation, all that in one go. Because if you think about most, you know, deep networks and deep models kind of specialize in some type of, you know, unless they get really sophisticated or they're, you know, they do pre-training like a ChatGPT where they can be versatile, but it still is kind of focused in on, you know, inferring from text and generating a response from text. You know, so you can kind of see like, you know, that's a pretty simple, you know, input comes in, it convolves and goes from there versus input comes in and, you know, goes somewhere, it does something, but it works well. I've used it a few times, as a hobby. I've used some of the the older YOLO models that are permissive for commercial use. I've used them before, and they work well, and you can, it's impressive because you can download that model and you can download a pre-trained data set. And, you know, I did that one morning. I had to detect a drone landing vertically as a camera watched it from below while the drone was landing with the sun behind it. So, you know, you have to figure out how you know, see a drone coming vertically at you if the camera's pointing up and the sun's behind it. That saturation gets intense there. And, you know, maybe about an hour, you know, grab the code, grab the model, grab the data, it, you know, had something that could, you know, if it saw the drone, would track it pretty much better than the video I was showing there. It was pretty, you know, on the nose, even in sunlight. So, you know, but trying to recreate YOLO from scratch is something I've been actually trying to do for fun anyway, and it's hard, so. But the main gist of this, you know, I guess maybe to answer a side question is, a convolutional network is it approaches a classification problem, and that's what you see kind of on the right. You know, this is, can I make this bigger? Slideshow. Yeah, so on the right here, this is essentially a multi-layer perceptron. This is that basic model over neuron that came out in like 1946 in Navy papers that we just couldn't test until the 90s because iterative computation was expensive and non-existent at that point, which is a classification network. So just, you're trained on something, give me, you know, here's an input, give me an output for it. And all this does at the front is basically pre-processes that into something you can understand in a classification sense there. So it's pulling out like, you know, what is the meaning of this picture? What is the meaning of the tank picture? What's the focal point? What's the feature? And then it's comparing that versus a list of things it's trained to know. That's all like a convolutional network basically does in the gist of it. And it just pulls those features out using, essentially, you can even see the math down here, you know, is very convolutional, a convolutional equation like. But it's just building up, you know, a feature-rich image, essentially. So hopefully that kind of maybe that made answer your question to a degree.
Sure. I was also wondering, like, you also mentioned getting like data sets. Where do you look for those?
I'm trying to word this in a specific way. You have to be careful with your data sets and where you find them because some of them are not permissive, especially for commercial use. And some companies will have them. Sometimes they will be provided in the case of something where you might be targeting a specific vehicle. You know, if you know, I guess to not beat around the bush, if you're building something that's tracking a enemy aircraft, then your signal intelligence and signaling guys may actually have data sets of this is what this looks like visually, this is what this looks like from a radar signature, and that's not information you would be getting without, you know, clearance and people going, hey, this is, you know, because if, you know, if the people who had that enemy aircraft knew we knew what it looked like, they would probably just change it, you know. So you would do that, put it in something like this, and that's a little bit of what Leidos would do there. You know, they had classified projects and they would train on, you know, unclassified clear data, you know, like, oh yeah, here's it flying over cities and stuff. And then, you know, they would take it into the closed room and they would retrain it, and it would be, you know, data of it flying, you know, of like planes that have flown over, you know, enemy territory basically. And because a city is a city is a city, even if we as humans put, you know, that's a bad city and that's a good city on it, the computer doesn't care. It's just as like, that's a city. I know I need to navigate and understand what a building is and what a person is, you know, what the meaning of, you know, the people down there ideologically is doesn't matter to all that. So, you know, sometimes you'll be given it. There are some open source data sets, and if you're doing academic work, there's a lot of benchmark data sets that go, you know, hey, this is pure and clean, and we keep this up just so that someone can train it and learn it. Back. This one is, that looks like MNIST to me, which is kept by a university. It's a handwritten digit data set. And it's a good benchmarking. If you do anything with like deep networks, that's a great benchmarking, like for classification. And it's kept up by universities. It's like some number of gigabytes there, but it's like 80,000 handwritten digits or something there, or like 80,000 per digit or something like that. But it's great, and it gives you lots of variation. It's a very well kept, well maintained statistical data set. So, you know.
Does Microsoft still have their general purpose imagery data set out there for open use? Do you know?
That might have been taken off, or they may have a reduced set they give to public people, since they have AI stuff too. Most companies that are doing big AI stuff probably have something, you know, internally, especially if it's specific stuff. Alternatively, and I don't recommend this, you can just let the thing loose on the open internet and just scrape data, you know, but then you get the problem of, you know, poison data sets there, and, you know, that can be both malicious and adversarial poisoning, but also just, you know, you're training your AI with AI images, and suddenly, you know, the 6-hand AI generated person now has 7 hands. It's like, oh, well, I'm gonna make mistakes upon mistakes there, and so I would recommend that. Also, there's a lot of copyright stuff floating about it, you know, is it legal to just pull the data everywhere and throw it into an AI, you know, AI art controversies, things like that. So that's kind of, and that's where the benefits of an algorithm like this potentially is you make this more sophisticated and you improve it and you optimize it. You're not on the hook for trying to train a network. Because training a network to do, you know, sophisticated tracking, I mean, that is a long training time. I know at Leidos we had some models we were training that took months and months to train just for the training phase on nice computers too. And, you know, being a defense contractor, sometimes the company doesn't buy backup power supplies. Sometimes those runs crash after 6 months. And sometimes people get very upset about that. Not me though, so. But, any other questions? Yeah.
The other thing you talked about is visible light spectrum. Is there anything that changes if you were to use infrared?
No, you can, because that's the point. You know, you can easily have your IR, infrared, optical wings, you know, the ability to see things we can't normally see, to translate that. So, and that's the thing, you know, when you get something like this, you get, and this is where that support GitHub as well, the one that uses the Kalman states, you can get in, so you can start using those in ways where you have fused sensors, right? You know, you have your optical, you know, like optical and IR and night vision, all that, to get a better scope of what does that target look like across, you know, a whole spectrum. You can also do stuff where you have cameras at different locations. So, you know, if you have like, think of, you know, the ship thing here, you know, obviously you're flying down toward that fleet and probably moments from being past tense there, since that's like the US Navy. I think that's the US Navy. It looks like it might be one of ours. Someone can probably correct me if that's not true. But all of those ships have cameras and tracking things on you from different angles, and they can communicate that and go, hey, you know, here's what that image looks like, that composite image. And I've worked with some people that, you know, made careers out of making composite imageries out of like, here's optical and here's a radar signature and here's, you know, laser targeting and near IR, and making a composite model that they can track and follow that would work in this algorithm that's basically fused and doesn't actually exist because it's elements from a whole bunch of different spectrums and light sources. So yeah, I mean, anything with you know, any camera type stuff, anything you want to do with that, and then the tracking, you know, you could be blind with that. That could be just a radar tracker. So I mean, you're doing the same thing in the software, you know, and what you would do with the you know, if this was radar, is you would have you know, that last box at the bottom there, the tracked object XYZ, you would send that as a set point to a control program and go, hey, you know, if it's a radar dish, you know, tilt it to try and follow, you know, send that as your set point and go, I need to follow and rotate, or, you know, if that's your, you know, a missile that's following something, go, hey, you know, I need to, you know, vector this way to try and hit that target. So. Anyone else wanna roast me? Have some conversations? This guy wants to roast me.
Let's give it up for Sean. One last chance if you want the code on the, yeah, pull up the code again. Boom. If you want the code on the GitHub, we will provide this via that form, so you can swap back. Give them a taste. Don't give them a...
Yeah.
So last chance to fill that out. Additionally, we have one more talk this semester. It is stealth design principles. So it'll be, basic topic will be, the whole slide deck will be, I will take a plane that is abysmal at stealth. Yes?
Is that a rehash from last semester?
No, it's an extension. Yeah.
Okay.
Yeah. But basically, we'll start with an absolutely abysmal platform like a Boeing 737 in terms of stealth. And it's just a terrible one. But so we're going to take that and we're going to go through. You are an aerodynamicist, you are a stealth engineer, you're a low observables engineer. How do you make this not get shot down immediately? And we will go through and fix its design. We'll fix its shaping, we'll fix its materials, we'll fix all that stuff up. And hopefully by the end, you can like somewhat understand what you're looking for in terms of stealth design. And once you get to a certain point, you can actually look at any plane and be like, that shit stinks. That's awesome. So that's to go with that. I'll be presenting that one. And thank you everybody for coming. We'll be around. You can come chat if you'd like. Otherwise, see you next time, hopefully.
Fix this.
Fix it. We're gonna fix it.